Hello everyone. Alright, welcome to the first episode of OPAD, one paper a day. Today we're going to do a paper on machine learning in healthcare. As this is the first video that I'm uploading, just going to talk a little bit about the structure of OPAD episode. It will start off with me just reading the paper in verbatim. Then we'll go through some summary as well as learning points, and I'll just give my thoughts at the end of the video, and that will be it. Right. So if you have any thoughts on how you think I could improve the process, feel free to leave a comment. Alright, let's jump right in. Okay, so today's paper, we're going to talk about this particular paper published in 2019. It's machine learning for healthcare paper, MLHC, right? The paper is titled "What Clinicians Want: Contextualizing Explainable Machine Learning for Clinical End Use." So this is a really important topic, right? Because I think in general we have a lot of need to translate good, especially machine learning models with good performance, all right, into the clinical setting. And I think there are a lot of barriers, and hopefully we can find out some of these barriers, what some of these barriers are in this particular paper, and how there could be potential solutions to it. Right, so translating machine learning models effectively to clinical practice requires establishing clinicians' trust, explainability, or the ability of an ML model to justify its outcomes, and assist clinicians in rationalizing the model prediction has been generally understood to be critical to establishing trust. However, the field suffers from the lack of concrete definitions for usable explanations in different settings. To identify specific aspects of explainability that may catalyze building trust in ML models, we surveyed clinicians from two distinct acute care specialties, intensive care unit and emergency department. We used their feedback to characterize when explainability helps to improve clinicians' trust in ML models. We further identified the classes of explanations that clinicians identify as most relevant and crucial for effective translation to clinical practice. Finally, we discern concrete metrics for rigorous evaluation of clinical explainability methods. By integrating perceptions of explainability between clinicians and ML researchers, we hope to facilitate the endorsement and broader adoption and sustained use of ML systems in healthcare. So that is the abstract. So let's look at the introduction now. For clinical machine learning, lack of model robustness, complexity of clinical modeling tasks, and high stakes are some of the technical barriers to practical adoption. Additionally, even a highly accurate ML system is not necessarily sufficient in and of itself to be routinely utilized and endorsed by clinical staff. The uptake and sustained use of ML in healthcare has been more challenging than anticipated, as observed through piloting models for cardiac arrest and sepsis. This brings about the question of how truly reliable ML systems can earn clinicians' trust for sustained use and positive clinical impact. Currently, many rule-based assistive tools such as different early warning systems have been deployed in clinical settings. By their very nature, rule-based algorithms are not considered opaque and need to be endowed with auxiliary explanations of model outcomes. However, recently developed ML-based tools that aim to improve on rule-based systems are not considered to have the same level of accepted transparency. Therefore, understanding ML model behavior beyond conventional performance metrics has become a necessary component of ML research, especially in healthcare. This has led to the development of interpretable or explainable machine learning models as a measure to overcome barriers of trust and adoption. Unfortunately, as it stands now, this is a rather ill-defined problem. Existing work suffers from significant criticism due to a lack of objective definitions of what would validate a model in terms of explainability in the context of clinical practice, while only limited works focus on evaluating the quality and usability of the proposed explanation methods for the target end user. The ML community has largely resorted to developing novel techniques for model explanations that are often insightful only to the algorithmic experts. Recent commentators have suggested that perhaps the explainability literature as it stands requires a pragmatic lens to better suit the needs of the end users, who are ultimately the ones who will decide if the model survives in the real world or not. For the purpose of this manuscript, we define explainability in ML for healthcare as a set of measurable, quantifiable, and transferable attributes associated with an ML system targeted for clinicians to calibrate model trust. Our goal is to synthesize a pragmatic notion of explainability for clinicians and effectively inform ongoing research efforts in clinical ML at our institution. The integration of clinical ML in hospital settings is prompting the application of qualitative methodology in a novel context. While previous work has assessed clinician use and acceptance of ML models retrospectively and through quantitative surveys, we are among the first to investigate prospective users' expectations of explainability. This method will enable us to anticipate potential challenges to translation, as well as to provide a baseline for future work to identify how explainability may evolve over time in conjunction with the sustained use of ML tools. Additionally, we aim to better understand which explainability methods can satisfy clinicians' needs. To this end, we conducted an exploratory pilot study with 10 clinical stakeholders to 1. Understand the role of explainability for clinical ML system, 2. Identify the classes of explanation that best serve the end user, emphasizing the context and diversity of their needs, 3. Characterize how these considerations can be addressed from an ML standpoint, 4. Propose metrics for evaluating clinical explainability methods and identify gaps and research challenges in the area. Technical significance: we identify when and how explainability can facilitate reliable dissemination of ML model predictions in clinical settings. We curate a set of concrete classes of explanations based on identified clinicians' needs. We evaluate this in the context of existing explainability literature to highlight gaps and research challenges for clinical ML. By highlighting clinicians' needs for explanations as specific technical properties, we hope to channel explainable ML research intended for clinical end use to tackle some of the challenge. So clinical relevance, near future will likely see increased adoption of ML solutions in key areas of clinical practice. Building trust between clinicians and ML models for higher uptake and satisfaction requires concerted and purposeful efforts from the ML community. This work attempts to preemptively identify clinicians' needs via research surveys to recognize concrete technical challenges that may be addressed using explainable ML with the objective of building reliable ML systems, fostering trust for sustained use, aimed at improving clinicians' workflow and practice. Alright, so that is the introduction. Alright, my initial thoughts are that this is definitely something which, a clinician requires. Alright, when it comes to the application of ML systems. Personally, I'm a clinician. I'm a MD by training, and we actually face a lot of issues with trying to translate these systems into clinical use, right? And I'm totally sold by the introduction on its thrust towards trying to evaluate and survey clinicians on what their needs are and how best to integrate ML into their daily workflow. Alright, so let's talk a little bit about the study design. Let's read that particular aspect. So study design, we employ an upstream stakeholder engagement method to address the aforementioned questions. Upstream engagement here means that a survey is conducted prior to or model implementation. Qualitative interviewing was determined to be an ideal method for exploratory nature of this work, as surveys are insufficient for capturing the conceptual complexity of the phenomenon we want to understand. Furthermore, interviews provide an opportunity to clarify participants' response and their reasoning. Interviews reach saturation defined in literature as the point where no new information pertaining to the main theme of explainability arose during the interviews, which is generally expected after approximately 10 interviews. We developed an interview guide to address the project goals. Conceptual development of explainability proceeded through the interviews to guide subsequent interview content. We interviewed 10 clinicians in 2 acute care settings, intensive care unit, ICU, and emergency department ED, with varying years of experience to develop notions of explainability and identify their need towards building reliable ML systems for their respective clinical practice. These settings were chosen because both departments are areas where we foresee implementation of ML tools to support clinical care. Additionally, both departments have current experience working with either early warning alert systems or opaque non-ML decision support tools. The following describes the upstream stakeholder engagement method and study cohort in detail. So the cohort, we approach a convenient sample of stakeholder clinicians who are familiar with ML-based clinical tools and are aware of ongoing developments in the field. Key stakeholders were defined as those who will be end users of the technology and whose acceptance will ultimately determine successful clinical translation of predictive ML tools. Given the diversity of target clinical tasks for use in the ICU and ED setting, 6 ICU clinicians and 4 ED clinicians were selected for the explanatory survey. These individuals, 5 male, 5 female, were both senior N equals to 5 completed residency training and junior N equals to 5 currently at residency training clinicians to ensure the spectrum of relevant experience was represented among the stakeholders. Discussions were held at the Hospital for Sick Children, Toronto, Canada over a 3-week period at clinicians' convenience and were recorded to facilitate recall accuracy. So let's talk a little bit about the procedures. Clinicians' views were solicited to assess the concept of ML explainability with respect to their medical setting. Each interview lasted approximately 45 to 60 minutes. Our interviews began by exploring clinicians' notions of explainability to determine what each clinician understood by the term and why he or she expected from ML methods from a specific clinical setting. We then introduced the clinician to a hypothetical interactive scenario based on their specialties, representing an ML tool incorporated into their division. For the ICU, we introduced a cardiac arrest prediction tool that reports risk of upcoming cardiac arrest. For ED, we introduced a tool that predicts an acuity score based on triage reports. We correlate a range of possible responses that may arise when considering different aspects of model behavior. So the hypothetical scenarios that are presented for SU, we suppose a machine learning based model has been integrated into the AHR system of the hospital. As vital measurements are being constantly recorded in the ICU, this model predicts the probability of a patient having a cardiac arrest within the next few minutes based on temporal vital measurements. The risk score is updated every few minutes based on the patient's current condition. Let us say a patient in your care is being monitored by the model and you receive an alarm that notifies you that they are at imminent risk of cardiac arrest, but you had not suspected CA for a given patient at that moment. ED, a machine learning based model, has been integrated into emergency department in your hospital. This system ranks incoming patients based on acuity using the information from the first triage. A patient in your care appears generally well, but the acuity score puts them in a high risk category. To enhance our understanding of the concept of explainability and trust as perceived by clinicians, further questions for us elucidate the following constructs. How will the clinician go about evaluating the validity of an alert in terms of translating into clinically actionable information on the part of the patient? How does this evaluation compare to other common non-ML tools such as alerts, risk scores, or other notifications concerning a patient's status? What do you currently do when one of the alerts, scores, notifications tells something that you weren't expecting about patient? What information would you want about system? Additional questions are detailed in the appendix. So ethics statement, our initial exploratory investigation aligned with the Tri-Council policy statements, TCPS 2, governing research-related activities in Canada, Article 6.11 and 10.1 stipulating activities exempt from research ethics board approval. Activities exempted include feasibility of the research, established research partnerships, or the design of a research proposal. Right, so just some thoughts after reading section 2, like how I've done for section 1. I thought that this particular study design I think it's based on some really rigorous and robust at least from the surface of it. I'm not an expert in the area of conducting research with interviews. I've never done such a research before, but it seems like they have looked at the current literature and look at what are some of the ways to conduct the interviews properly and to ensure that the interviews that they conduct for the various clinicians, they are of a good composition, right? In terms of the ratio, like in terms of the gender ratio, the seniority ratio. If there was any criticisms I have for this particular part, I would think it would be the sample size. All right. I do appreciate that it's difficult to get a high number of clinicians to be part of the interviews, and conducting interviews definitely not a non-trivial task, because each interview lasts about 45 to 60 minutes. So to conduct this study, you probably have to set aside a day, about at least 2 to 3 days. Spread the interviews over 2 to 3 days to conduct this 1 hour long interviews. I think that's my criticism. Other than that, I find the scenarios clinically appropriate. Okay. As a clinician myself, I have not rotated for a significant period of time in ICU and emergency department. But I think looking at just the generic approach to how they have developed their vignette, I think it's very reasonable. And questions asked, I suppose we have to explore the appendix to look at it in greater detail. But I think at this stage I'm comfortable with this set of questions. Alright. Okay, so let's look at the results. We organize the results and analysis of the study as follows. We identify concrete and measurable set of explanation classes curated from the qualitative assessments of the surveys. We identify a few metrics that help assess the utility of any class of explanation to assess clinical utility in section 3.3. Finally, we summarize how existing explainable ML literature fares in the context of the clinical ask. A full synopsis of the qualitative data, including illustrative quotes, is provided in the appendix. What makes a model explainable for clinicians? Throughout the exploratory interviews, it was clear that the clinicians view explainability as a means of justifying their clinical decision making, for instance, the patients and colleagues in the context of the model's prediction. To provide these explanations, all clinicians express the need to understand the clinically relevant model features that will align with current evidence-based medical practice. The implemented system model needs to provide clinicians with information about the context within which the model operates and promote awareness of situations where the model may fall short. Models that fall short on accuracy within acceptable as long as there's clarity around why the model underperforms. While it is ideal to learn models based on much contextual information, it is not always practical, and clinicians are aware of such a possibility. Furthermore, the complexity of clinical medicine is such that no model is likely to achieve perfect prediction. Clinicians, in fact, expect this, and acknowledgement of this challenge promotes trustworthiness. Clearly specifying features that go into the models of decision making is a way to facilitate trust in the model, as well as directing use in specific patient populations and determining parameters guiding appropriate use. The relevant quote, the variables that have derived the decision of the model, was brought up to 3 ICU-1 ED clinicians. This type of transparency is also identified in Mitchell ETAL 2018 as being crucial and needs to be disclosed to ML model users. While familiar metrics such as reliability, specificity, and sensitivity were important to the initial uptake of an AI tool, a critical factor that continued usage of said tool was repeatedly successful in prognosticating the patient's condition in their personal experience. Real-world application was crucial, developing a sense of when it's working and when it's limited, which meant alignment of expectations and clinical presentations. So clinical thought process for acting on predictions of any assistive tool appears to consist of 2 primary steps following presentation of the model's prediction. 1, understanding and rationalizing the predictions. Task classes of explanations for clinical ML models should be designed with the purpose of facilitating understanding and rationalization process. Clinicians believe that carefully designed visualization and presentation can facilitate further understanding of the model. These features are essential to sustained model use, largely due to the immediacy of the clinical picture being captured in the context of multiple competing attentional demands that require user-friendly visualization. So discern that there are situations where well-designed visualization is not enough and only additional explanation can facilitate and fill the gap in the identified clinical workflow. How does this translate to reliable clinical ML design? We determine that our decisions determine from our discussions that a well-designed explanation should augment or supplement clinical ML systems to recalibrate clinician trust of model predictions, provide a level of transparency that allows users to validate model outputs with domain knowledge, reliably disseminate model prediction using task-specific representations, e.g. confidence scores, provide parsimonious and actionable steps clinicians can undertake potential interventions or data collection. We further curate the following cases of explanation from qualitative assessments that clinicians identified to most effectively complement model predictions based on our survey. We highlight wherever necessary the applicability and importance of each explanation class for different settings, ICU versus ED. Feature importance. Clinicians repeatedly identified that knowing the subset of features deriving the model outcome is crucial. This allows them to compare model decision of the clinical judgment, especially in the case of a discrepancy. In time-constrained settings such as ED, important features are perceived as a crucial metric to draw the attention of clinicians to specific patient characteristics to determine how to proceed. While multiple clinicians mentioned the need to know relevant variables driving a prediction, see Appendix B, a junior clinician mentioned you have just a number, you can still use it. But in your mind, when you put all the variables that you take a decision, the weight of the variable is going to be less than if you do understand exactly what that number means. It's also important to note that clinicians expect to see patient-specific variable importance as well as population-level variable importance. While an extensive survey of feature importance is beyond the scope of this work, we highlight that patient-level feature importance is a challenging and far less explored machine learning problem. Instance-level explanations. Among commonly researched explainability methods we investigated part of our interview is whether data instances as explanations are useful in any clinical setting. Clinicians view this as finding similar patterns patients and believe that the kind of explanation can be only helpful in specific applications. For example, in cases where an ML model is helpful in helping clinicians find a diagnosis for a patient, it's valuable to know the samples the patient has previously seen. However, in time-constrained settings such as ICU or ED, did not find explanation technique appealing. A non-trivial challenge of this class of explanation that researchers need to be aware of is the definition of similarity that is used. Clinicians identified that despite similar outcomes, patients may differ significantly in the clinical trajectory to arrive at those outcomes and vice versa. Various definitions of similarity may be proposed depending on the task the model is performing and the way the user wants to use the explanation. For example, some clinicians were interested in seeing similar samples to their patients because they were curious to know what actions were taken in those cases and the associated outcomes of the interventions. Uncertainty. Clinicians overwhelmingly indicated that the model's overall accuracy was not sufficient as clinical judgment and their judgment often determine their sustained use and trust in the model. This is to say that each time an alert presents a prediction, clinicians will anticipate a clinically significant change in the patient's status that should ideally align with the model's prediction. Previous reports have indicated that despite determination of expert agreed threshold for triggering alerts, there are still many alerts not accompanied by clinically actionable change, which undermines use and endorsement by clinicians. This point holds particular importance for clinical ML to ensure developments align with clinicians' expectations to promote trust and sustain model use. Presenting certainty scores on model performance or predictions is perceived by clinicians as a sort of explanation that complements their output result. Sorry. Just accidentally click on a link. Let me just go back to that spot. Yeah, so we're at uncertainty, right? Right, so this issue is ubiquitous across healthcare contexts and requires careful consideration by model developers so as not to perpetuate clinician disillusionment and disengagement with the system. This makes calibration of complex models a significant technical challenge that needs to be addressed for clinical practice. Additional challenge is the fact that even models performing acceptably on average can have significant individual level errors, which is undesirable in clinical practice. There are two sources of uncertainty we highlight that can affect model trust. Model uncertainty of model parameters that best explain observed data is known to be a significant source of uncertainty in model performance. Modeling for this uncertainty can be achieved by actively accounting for distributional differences during training. Few of these methods have been actively co-opted in clinical healthcare for explainability, but nonetheless are crucial to uptake. In addition, model misspecification refers to performance deterioration due to a misspecification of the model class during training. It can lead to an overall underperforming model and can further reduce the effectiveness of this model used for dealing with model uncertainty. This problem is especially understudied for time series models that heavily employ deep learning methods, and to the best of our knowledge remains mostly unexplored in clinical healthcare employing deep learning methods. Data uncertainty. This sort of uncertainty can from noisy missing data on an existing inherent uncertainty in the data. Both of these challenges are commonly faced in clinical ML. Inherently uncertain observation can be, for instance, a complicated patient with different diagnosis. Thus is considered a relatively more difficult problem. Characterizing consistency under missingness has been only briefly studied in supervised classification system and needs to be rigorously adopted and evaluated for clinical applications. Temporal explanation. So patient trajectories that are influential in driving model predictions was reported to be an important aspect of model prediction. This area remains relatively unexplored in clinical ML explainability literature for a few exceptions, focused primarily on attention-based and sensitive analysis mechanisms on deep learning. However, explanations based on attention mechanisms can produce inconsistent explanations. Explainability for temporal data is a relatively challenging task as it requires analyzing higher-order temporal dependencies. ML models that perform such predictions should be able to explain their prediction based on changes in individual patient state. In units such as the ICU, clinicians are interested to see a change of state that has resulted in a certain prediction. Note that this is also related to explanations using future importances. Subsection 3.2 is a necessary component of providing explanations in the temporal domain. To the best of our knowledge, not much has been investigated in this domain as formal definitions of explanations. Transparent design. Clinicians pointed to the need for models that reflect a similar analytic process to the established methodology of evidence-based decision making. They anticipate model decisions with similar emphasis on recognizing the clinical features driving the prediction as being more interpretable, since it reflects how they currently assess a patient's risk status. Translating a model to transparent design, e.g. a decision tree, is useful to facilitate rationalization of model behaviors expressed by one ICU clinician, which want the equation to know what the weights are. But if it's a variable and knowing that there's too much detail, then it's just not that helpful. And if there's a discrepancy between the current clinical protocol and the model, we don't know what that is occurring, we are going to be very nervous. To the best of our knowledge, this is the most well-studied area of model explanations in general and clinical ML literature. For example, a variety of rule-based methods have been proposed significantly for purpose of transparent clinical design. Model distillation refers to learning a simpler model class that can perform at par of a complex ML model and be considered as an attempt towards transparent design. Closely related are regularization-based methods that attempt to regularize models for enhanced interpretability. These methods tend to assume that there are trade-offs between model performance and their perceived explainability. It's unclear when such a trade-off is acceptable, especially if it amplifies individual level errors. We further argue that such models should be rigorously evaluated for performance under other factors like misspecification of the distilled model or regularized model, induced biases, and general uncertainty to facilitate reliable adoption to clinical practice. So the 3.3, in section 3.3, they look at metrics for evaluating explanations. So we further identify that explanations intended to build trust in clinical setting could benefit from being rigorously evaluated against the following metrics. Domain appropriate representation. The quality of the explanation should be evaluated in terms of whether the representation is coherent with respect to the application task. For instance, for patients in the ICU, clinicians already have a lot of context as to why the patient is currently admitted to this division. Explanations that are redundant to the ICU task are not desirable unless critical to potential clinical workflows. The interviews review a diversity of settings in which clinicians operate, like diagnosis versus cardiac care management. See instance-based explanations in section 3.1, which determines the representation best suited for appropriate settings. The representation itself should not further obfuscate model behavior for the clinician. This, for instance, requires careful filtering of the information most useful at any instance, highlighting age even if it's not an important feature. The type of explanation will largely be evaluated by rigorous user studies involving stakeholders. Potential actionability. Given a model that satisfies minimal trust-based criterion has been sufficiently evaluated for performance, any complementary explanation should inform follow-up clinical workflow, including rationalization or model prediction. This follow-up can be anything ranging from checking on a patient, ordering additional lab measurements, or determining an intervention. Overall, in an applied field like clinical ML, explanations that are informative in terms of understanding the mode but have no impact on the workflow are of less importance. Similarly, the explanation should be parsimonious and timely. The nature of explanation should also account for interdependent factors that inform its usability. This can be determined by the purpose it can serve in any specific settings. For instance, ED clinicians believe that any risk assessment tool will help them allocate resources appropriately. Therefore, explanations provided for the ML model should facilitate the decision making. For instance, in an ICU setting when time to action is extremely important, counterfactual explanations of patient similarity are not informative, usable, and result in cognitive overload. And lastly, they talk about consistency. So consistency refers to two factors. The set of explanations should be injective or changes in model predictions should yield discernible changes in the explanation. These changes should be invariant to underlying design variations and should only reflect relevant clinical variability. Explanations that are inconsistent across any of these factors effectively violate their reliable actionability and also negatively impact the trust of clinicians. Consistency is also closely related to robustness of explanations. For instance, such lack of consistency has already been identified using statistical methods or commonly used explanation techniques in deep learning literature outside of clinical ML. What is missing in explainable ML? So while a multitude of novel explainability methods have been proposed in the literature, they may not be directly applicable or be significantly tailored to clinical settings in the context of ASK outlined in section 3.1. In the following, we focus on identifying a collection of existing state-of-the-art methods which can be used to generate explanations that are usable for clinical stakeholders. We summarize our results in Table 1 and identify possible shortcomings of existing ML approaches for clinical usability and relevance. Note that while a complete review of existing explainability methods is outside the scope of this work, we highlight the most relevant and popular techniques in the context of the classes outlined above. Note that even if an existing explainability method is evaluated in a clinical setting, a rigorous evaluation of these methods for robustness and other interdependent factors still necessitate sustained research. Additionally, as noted in Section 4 and Table 1, some methods may work well for specific kinds of data, like images may have to be non-trivially extended to be applicable to other data and within the additional complexity of clinical settings. So with that, we finished Section 3. That was a very long read because there are many things which are covered. So let me just go through some thoughts I have about this particular section. Well, I thought that the parts where they focused heavily on specific quotes that the clinicians have given were really interesting because that sort of helped the researcher who does machine learning research to contextualize, right, how their model should be explained, alright, especially with such a heavy focus, like in machine learning, the focus has always been on performance, and a lot of these metrics that are out there are focused on how sensitive, how specific, how accurate, or how discriminative the model is. So having like sort of a change, right, in terms of what the focus should be, right, by using all these quotes that they have gathered from the interview, I thought was a very fresh perspective and approach to looking at explainability in machine learning. What I like to focus on is, I think, the bold points and some of these bulleted points, right? And I'd just like to give a few comments on each of these points that have been highlighted, especially in section 3.2, right, where essentially they want to look at how you can translate their insights from the interview into reliable clinical ML design. I think point A, it talks about recalibrating clinician trust and model predictions, right? I think that sort of makes sense because a huge part of the paper actually talks about how clinicians sometimes don't really look for that best performing model, alright, in order for him or her to trust the model, but rather they want to have an understanding of how those model predictions, why some of these model predictions were made erroneously, alright, and how some of these predictions are made correctly, right? By having that level of understanding, they are able to recalibrate their trust and be able to develop a better use case for the model in the clinical setting. And I thought this is the second point. Onto the second point, I thought that was fairly interesting to look at validation of model outputs of domain knowledge. And I think that's something that I I can do easily, all right, as both a clinician and a machine learning researcher, right? So that is easy for me because I do it all the time, all right. Whenever I develop a ML model, I correlate with my clinical understanding of that specific um, clinical problem statement that the model is trying to solve. All right, um, and I sort of can explain and I can validate those outputs easily. But I can see why this could be a big point. All right, especially for uh, the 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 researchers who just do machine learning research, right? Because they wouldn't be able to have that domain knowledge to understand that their model actually don't make sense, all right? And pushing the model to the clinician would therefore not be useful, all right? So in the context of someone who does just purely machine learning research or just and focus on using this model for a clinical problem, then in that context, collaboration will have to be very important. Alright, for I would say it has to be a mutual validation process where the clinician validates the model and the data scientist sort of validate whether a particular clinical problem statement that the clinician has proposed can be actually solved with modeling. Point C talks about reliably disseminating the model prediction using task-specific representations. Like an example given was confidence scores, and I thought that's a given. All right, but I do note that actually quite a few machine learning research don't actually give confidence scores, right? Confidence scores and and basically like all these different like like a t-test and the different sorts of tests for significance. I think these are more commonly used in a clinical setting, and I believe this in no means is a criticism to the ML research that's out there, but having those uncertainty markers there will definitely help to improve trust that this specific model accuracy that the machine learning researcher is proposing is actually something that is believable. The fourth point, it talks about parsimonious and actionable steps, right? And I think this is something which is really very controversial because when we talk about something that is parsimonious, right? You know, there are two ways to look at it, right? One is that are you talking about the features being parsimonious because they're picked by the experts, right? And therefore they're the most parsimonious in the sense that they're the most clinically relevant kind of features that should be included in the data, should be included in the model, pardon me. Okay. And the other way to look at parsimonious models is to look at feature selection, right? The different ways to do feature selection, like select k-best, or do like recursive feature elimination, alright, or do some kind of singular value decomposition to compress the entire feature space into a few features, right? But that will lose interpretability in that process. So there's a lot of techniques, a lot of ways, a lot of approaches to do this step of do this particular step of selecting features for a parsimonious model, right? And I thought that is a very good point to have, but personally, if you ask me, I believe in a more data-driven approach rather than an expert knowledge-driven approach, despite me myself being a clinician. And the reason why I say that really is because I think as clinicians, we can be very biased towards our own anecdotal clinical experience, right? And I would prefer the data to drive the feature selection, and for that to be a validation process, so the clinician to basically validate whether those specific features that have been picked up through the data-driven approach, whether they are appropriate for modeling. So so my other thoughts on the other parts, specifically the both parts: feature importance, instance level explanations, uncertainty, and temporal explanations, transparent design. I think those are things that I can easily agree with. All right. Although I really cannot comment much on temporal explanations because I don't do a lot of I don't do a lot of machine learning in healthcare research that is dependent on temporal data. All right. But I do like to focus a little bit more of all these bolded words on transparent design, right? Because that is something very close to my heart, right? And a lot of these things that have been discussed, like looking at how there are trade-offs between model performance and explainability. These are actually very. This is a very common problem, right? When we try to develop something which is transparent, it often comes with that kind of cost, and that kind of cost is really due to the fact that we are regularizing, we are doing methods which reduce the complexity of the model, alright, and really try to water it down to a few important features or a few important pathways that can explain the model itself, right? The other thing that I don't really agree with, alright, since I'm talking about things that I'm disagreeing with the article on, I suppose this is like the criticism section. Is that there are certain parts over here that says that like translating a model to a transparent design, and they give an example as decision tree. I don't really think that decision trees are really can be considered as a method that facilitates rationalization on model behavior, particularly when you have a gradient boosted ensemble decision tree, especially when you have ensembles, whether it's random forest, gradient boosted decision trees. They're all it's 100 trees, and each of these could be like 5 or 6 levels deep, alright, and it's just very messy and is randomly picked. There's no chronology in which it is picked, and the dependence within the tree itself doesn't really make sense. Alright, that's my own personal experience with decision trees. Alright, even if you do a single decision tree, alright, with a reasonably large depth, and you will run into the same problems. It's not. I mean, it is humanly interpretable, but it is not clinically interpretable. That's how I'll put it. Right, it's humanly interpretable because you can see how the individual decisions have made, but because in a clinical sort of domain, we want more than just that. We want to go beyond just being able to read the model and its decisions. We want the chronology of decisions to make sense. We want the chronology of the individual decisions in the decision tree to make sense. That's what I mean, actually. And also for all those like individual splits that you have in the decision trees to sort of correlate with clinical knowledge, which I find very hard to achieve in our current state of the art. Alright. Another criticism I have about this section 3 is that I don't see Scott Lumberg's work, or like he and his colleagues from University of Washington referenced here. Alright, so I thought that it's such a big topic nowadays. This is a paper published in 2019, and Shapley game theoretic values, or otherwise known as SHAP, has been around since 2017. So a huge disappointment for me is probably them not discussing or referencing them, alright, in terms, especially when they talk about instance level explanations, and they talk about feature importances, alright, because that's what SHAP is mostly created for, right? And I think those are very important things to discuss, right? Okay, so about the different metrics for evaluating explanations, I think that's the last part before we move on to section 4, the related work. When I look at the matrix, they talk about, I think, a three main matrix. They want to look at domain appropriate representation, they want to look at potential actionability and consistency. I think these are not things that I would disagree with, but I think domain appropriate representation is something which is extremely difficult to achieve for the data scientists and the machine learning researchers, right? And the reason is because the data sets out there are just not built for this, right? Let me give you an example, right? A lot of people use Mimic 3, Mimic 4 data set. It is a huge data set where there are thousands of patients, tens of thousands of patients, and Mimic, the long form, is known as, if I'm not wrong, is something information mud for intensive care, right? Something like that, right? And that particular data set is very rich. You can get all the lab values. In Mimic 3, you can even get the discharge notes. You can get all the echocardiograph reports. You can get all the X-ray reports. It's just extremely rich, right? You have every single sort of vital sign that's been plotted in ICU, or even they give you some of these vital signs that have been plotted even before they went to ICU in the general ward or even emergency department, right? It's a rich data set, but the problem is that in clinical research, in order for us to apply a specific model to a clinical setting, it has to be something, the cohort has to be rigorously chosen. It has to be very well curated, in the sense that your age of inclusion, for instance, right? Your inclusion criteria for age, for the kind of patients that with the specific kind of diagnosis that you are looking at. All this has to be very clear, and the cohort has to be selected based on this set of criteria. All right, and it's only with that kind of assurance that we know that this model that we are looking at is domain specific and is domain appropriate. And my criticism, not of this paper, but of our current, more of today's current state of the art, is that a lot of the data sets that we have are still at the toy stage. They are not really worth that level of they're not really expanding to that level of providing very quality data sets, for domain specific quality data sets for the researchers to work on, right? And that is important, right? And for all these curated data sets to be out there is important, because we need to benchmark new algorithms, all right? Especially those who have promises or claims that this is something that is generalizable, and it's very hard to believe these papers even when they're accepted to good quality journals, because good quality machine learning journals, right? Definitely not medical journals, all right? It's very difficult to accept that they can be used meaningfully in a clinical setting, because the kind of data section is just not rigorous enough, and in some sort of a view it can be seen as just a toy data set, right? I think the other things is very non-objectionable, right? Of course we need to have actionability, and of course there needs to be consistency for us to want to apply these models, right? Especially in a life or death setting for a patient. Alright, so we're going to talk about related work. Okay, so in this particular section, related work, to the best of our knowledge, no prior works have conducted target stakeholder studies to the specific purpose of identifying explainability challenges in clinical ML. In terms of translating ML methods to clinical practice, have extensively recorded their observations in piloting an early sepsis warning system to a single institute over a record of multiple days. A few user studies have evaluated prototypical electronic health record systems or associated visualization prototypes for efficacy of facilitating diverse clinical workflows. Herein, we highlight some state-of-the-art literature and explainable ML which we have discussed in terms of the relevance to adoption of ML models in clinical practice. Explainability in general, machine learning has focused on understanding model behaviors from different perspectives, although simpler model classes are considered more interpretable by users. General trade-off between model performances and explainability as assumed. Some methods like LIME and anchors, okay, they finally mentioned LIME, use simpler model classes to derive feature-level explanations. Abstractions such as data instances are used as a means of explaining model behaviors. Visualization is also explored as a method of providing an insight in model behavior. We characterize these methods as diagnostic methods as they are not necessarily targeted to provide explanations of the target user but focus on improving model understanding. Guidotti, sorry if I pronounced the name wrongly, Guidotti for an extensive survey of existing methods for explainable ML in general. It's very interesting that they call this a diagnostic method, right, rather than something that that really looks deeper into the model itself. Right. So here are some of the feature importances, instance level explanations. So this is just a table. I think these tables are really helpful. Right, so to talk about feature, first, they have included Shapley, right? Yeah, so that's what I'm looking for. Sensitivity analysis, RRP. Right, so uncertainty distributional shift, parameter uncertainty, temporal retain, influence, functions. But actually, I thought that LIME, anchors, Shapley values, all this should also be classified under instance level explanations, right? Because they do give instance level explanations, right? So it's fairly interesting, and yeah, feature level, yeah, correct. Okay, so and less powerful in I thought that transparent design itself can also include the LIME and CHAP methods. So anyway, let's continue reading this. In clinical ML, visualization systems have evaluated for efficacy of interaction between EHR systems and healthcare practitioners. Neural attention mechanisms are used for developing interpretable models for heart failure and cataract onset prediction, and tree-based regularization for sepsis and HIV treatment. While Wang and Rudin, Ustan and Rudin built rule-based or sparse linear methods for predicting hospital admissions and sleep apnea scoring systems, Ahmad ETL conduct the most extensive survey of explainable methods in clinical healthcare and analyze them in the context of existing notions in general ML, how to relate to clinical, discussing ethical questions thereof. They conclude that general agreement in the field of clinical healthcare to explainability is fairly low. Our work attempts to bridge some of this uncertainty by initiating a conversation with and conducting the needs of stakeholders. Several works have attempted to codify rigorous evaluation of explainability methods. For instance, in Doshi, Velez and Kim propose ways to evaluate interpretability methods depend on application type and thereby the nature of evaluation, while Narayanan and Prasabzi conduct user studies to understand the quality of many proposed explainability methods. Statistical methods have been introduced for evaluating the robustness of a few candidate explanation methods like saliency and neural attention architectures. So in discussion, this work documents the ongoing challenge of translation of clinical ML with a particular focus on explainability through the eyes of end users. We demonstrate how clinicians' views sometimes differ from existing notions of explainability in ML and propose strategies for enhancing buy-in and trust by focusing on these needs. In light of the objectives highlighted in section 1, we survey clinicians with diverse specialties and identify when explainability methods can assist in enhancing clinician trust in ML models. Our research survey involved creating hypothetical scenarios or developing a machine learning based predictive tool to carry out specific tasks in the ICU and the ED respectively. We demonstrate that by accounting for target stakeholders, even though the explainability task in clinical setting is significantly diverse, but it can be codified into specific technical challenges. We further outline the need to evaluate clinical explainability methods rigorously under the proposed metrics in section 3.3. To the best of our knowledge, this is the first attempt at involving ICU and ED stakeholders to identify targeted clinical needs and evaluating it against general machine learning literature in this field. Some of our non-technical observations, as highlighted in the qualitative synopsis in section 3.1 Appendix B, are corroborated to some extent by the observations of Elish, who followed development and deployment of machine learning-based sepsis risk detection tools in a clinical setting. Our work, however, is far more generalized. We concretely map conclusions from clinical surveys to prominent gaps in explainable ML literature as it pertains to effective clinical practice. Limitations of our methods are highlighted below. So limitations are research survey for identifying explainability challenges restricted to ICU and ED specialists. Most specialists we interviewed have reasonable knowledge of clinical ML systems. Given the research questions were focused on predictive tasks that identify challenges may only have limited applicability to wider class of ML models. Applicability of the identified class of explanations to other clinical settings needs further evaluation, while our understanding of or on exploration into research design of a broader study of explainability, we are able to glean useful insights. A strength of the study is that we attempted to elucidate concepts under the explainability framework that can apply to many novel ML-based implementations. A large research question we are currently pursuing is whether satisfaction of these explainability requirements is directly related to perceived usefulness of the tool as well as to sustained use and endorsement. We hope to develop a conceptual framework that can be utilized across the spectrum of ML tools that can support consistency and quality of ML's explainability requirements in hospital environments. So that's the end of the paper. So again, my thoughts, alright, about this section 4 and section 5. I suppose it wasn't really mentioned about SHAP and Lime. Really, is because of the fact that they were just evaluating what is required based on their survey findings, not survey findings, the interview findings, right? And a lot of what was not discussed then was about the current methods. So in section 4, it's a very nice section to sort of tie in, because they have identified specific classes of explanation which they think essentially will help to breach some of this requirements analysis that they have gotten from the interviews, right? And they sort of bucket current methods into each of these explanation class. To be honest with you, I was quite surprised by the uncertainty category, because I really thought that is what the author was trying to talk about was primarily about parameter uncertainty, but I suppose distributional shift is also a very important topic in machine learning and in general, actually, because it's not just about interpretability here. It's about how well the model can perform when it sees new data, right? And when the new data has a data shift, right? Obviously, the model would intuitively have a lower performance, right? So that was what I was thinking about when I look at uncertainty. I was really thinking about parameter uncertainty. I was not thinking so much about shifts in data. So I think that table, this particular cell over here, really clarified it for me. I think I mentioned in passing that I believe SHAP and Lime can be used for instance level explanations, can also be used for transparent design, but I suppose what they meant by transparent design is that essentially when you start the modeling, it has to have those considerations to begin with. What they are trying to say when it comes to transparent design is about like things like regularization or reducing the number of features and modeling based on a reduced set of features, right? So that you can improve the transparency of the particular model, right? Rather than looking at explanations, right? So I think that essentially is what it's talking about, right? I'm not so sure whether temporal explanations should be regularly used, alright, as an explanation class, because I would think how I would have used this paper, right, if I want to talk about explanation classes, is to say that we want to measure the explainability of my method, alright, with these 5 characteristics, right, and like I said earlier, most of the work that I do has no temporal, it's not related with temporal data, right? So this characteristic will automatically be not applicable, right? So I thought they would have wanted something more generic, right, to as one of the key characteristics that people need to fulfill, right, as part of this explainability paper. Right, so to talk about discussion, I thought it was they gave fair criticism to their work. But what I would also have said specifically about the specialist, right, that they have interviewed, is that it's actually to me it's the cohort that they have selected is there's a, it favors a specific part of the ecosystem, right? And there's actually a name for this, right? When it comes to study design, when you select specific patients, or you select specific people to interview, all right? Because it actually causes bias, all right? And I believe that I thought they would have mentioned this more explicitly, right, in their limitations, right? That this could be a bias that's introduced, right? Because you're interviewing, it's not just a bias arising from their it's just not just a bias arising from the fact that they are ED and ICU specialists, right? But it is biased because these people have prior ML research, they are aware of and involved in academic research, right? And basically they are familiar, and we actually want to reach to the people who are not familiar, right? And try to understand what what are those, like, big issues that we need to solve in order to encourage them to use machine learning models. So I thought that's something that's not addressed in the paper, right? That might be an unfair criticism, but that's just my take on it, right? Um, the strength of the paper, I thought, maybe it's because it's towards the end of the paper, and they didn't really mention much. I thought there were definitely, they were a bit modest. I thought there were a couple more strengths to the paper. But in general, I feel that they have captured the gist of it, is that that this is really first. I really think it's one of the first few papers. It is the first paper which really did an interview and try to understand, at least in some manner, systematically try to understand why there is so little translation from machine learning models to the clinical setting. So I suppose that's the reason why it was published in MLHC 2019. Alright. So that's it. That's the first one paper a day paper that we have done. I've read to you the paper, I've given you some of my thoughts. Alright. I was like I've said earlier, summary, learning points, and thoughts. Alright. After each section of reading. So that's it for today. Thank you for watching.